Well, good afternoon, everybody.
Sorry.
Good afternoon, everybody. Today, as Tracy mentioned, we're going to be talking about laboratory and fume exhaust systems. In particular, I'm going to spend a little time on fundamentals and best practices. My name is Matt Gaedtke. I am the segment manager of Greenheck's fume exhaust business, and I've been at Greenheck since 1994, so going on 28 years in the commercial and industrial business. My background is mechanical engineering from University of Wisconsin-Madison and a master's of business from University of Wisconsin-Oshkosh. And along with power roof ventilators and bathroom fans and industrial fans, my last about 12 years have been dedicated to laboratory exhaust systems. So our learning objectives today will
Hold on 1 second, Matt. Yeah,
no problem.
you have to share your screen again. I saw it from you earlier.
It didn't work? Okay, hold on. I will do that. Let me pull that back up. Here we go. Let me know how that works, Tracy.
That's it.
Fantastic. All right, so our learning objectives today, number one will be to just go over the fundamentals. And as you look at this photo on the right, you see some products that are mounted up on top of the roof deck. So we're primarily going to be talking about the equipment that's helping pull the air out of the lab space. But I do want to spend a little time not only talking about that equipment, but how that relates to the hoods inside of the space and duct pressurization. So we're going to jump into our virtual lab for a few minutes as well and talk about the overall functionality of how constant volume systems and variable volume systems work. To wrap up, we're going to go through some best practices. And when you're dealing with laboratory systems for 12 years, you run across different types of situations that engineers, owners, contractors run into. So I'm going to talk about a few of these things, what I've witnessed, ways to help your installations turn out better in the long run so that we have a safe operating lab space. So main objectives of a laboratory exhaust system are really summed up. If you get the ASHRAE Laboratory Design Guide, Figure 9.9, a great document to have on your desk if you do a lot of laboratory work. But really it comes down to a couple fundamental goals. Number one, for all of the people inside of that facility, we want to have a safe environment. So whether that's a process or chemical fume hoods, it's helping extract that contaminated effluent out of the space. And then as you can see on this diagram, I have a stack, and out of that stack is this effluent. And in this case, the wind's blowing it left to right across the page. So now we're equally concerned about air intake A and B, or if there are people up on top of the facility doing maintenance or other things on that facility. So whether it's in our building or outside of our facility, it's very important. And then really the third aspect is the environment literally around our space. So many of these labs it could be on a college campus, or there's just a lot of neighbors. And being good neighbors, we want to make sure that we don't do all of this work just to keep our building safe, but we want to keep that whole neighborhood safe as well. So it is life safety in and around our facility. Now, there are a couple of different aspects that define what these products should look like and how they're designed from a fan manufacturer perspective. So for simplicity, I'm going to start with NFPA 45, National Fire Protection. You can see the acronym description on the bottom left. You can see this gentleman standing on this concrete curb. And from the bottom of those fans to the top of the nozzles needs to be at least 10 feet tall. So the whole idea here is we're trying to get this effluent up and away from the building. This gives us some stack effect. And we'll talk a little bit more about the momentum component, but having that built-in stack keeps anyone from on the roof sticking their head or their hands in the airstream, because that could be potentially contaminated. Now, ANSI Z95, also ASSP, and again, those acronyms are here, has to do with the discharge velocity. And over the years, that was as simple as maintain 3,000 feet per minute. But as of this last March, ANSI Z95 has changed, and they've removed that minimum discharge velocity. And I'll read this because it's kind of a mouthful to go through, but it specifically says now, exhaust stack discharge velocity shall be efficient to reduce the concentration of hazardous materials in the exhaust to safe levels at all potential receptor locations. So what does that mean? Really, you have to look at all of your labs what's coming out of the labs, what are the conditions around that space, so concentrations, how challenging is that environment, and when that's discharging the nozzles, is that at a concentration that's of concern or not concern? So in a lot of cases on this bigger lab, this means getting in touch with a wind wake consultant to be that next set of eyes to make sure that you have an overall safe facility. For bigger labs, that makes sense. For smaller labs, what I would say is sticking with that 3,000 feet per minute, like we've done in the past, is a really good start. And as the lab becomes more and more of a concern in terms of location of neighbors and what you might be dealing with, again, talking to a wind wake consultant might be the approach that you need to roll. So keep in mind that's changed, and that's just been activated now for the last couple months in terms of ANSI Z9.5. Now, a couple things that are also taken out of that fundamentals guide. This is figure 9.8, and I'm bringing this back up because I'm seeing more and more of situations where we have field built or even other fan manufacturers potentially offering types of equipment that are not necessarily designed for laboratory systems. So I'm going to start on this bottom row here, and you can see it says poor, should not be used. And if you go back to the diagram I just showed you where I had a stack on top of the building, clearly having some type of gooseneck like we're showing here and this Q is not going to be a good solution, or the diesel stack cap. But I do see some manufacturers offering butterfly dampers or some types of stack cap for lab exhaust. Really, that's a no-no. We don't want to go that direction. Anything that impedes that effluent from getting up and away from the facility should not be done. So I'll skip up into the middle section and even the top. And what you'll find that in most cases, a simple straight stack with a conical discharge is one of the best approaches to use. Reduces the energy, helps get that effluent up and away from the building. So keep this in mind. A lot of it's common sense. Get the effluent up and away. Don't wash it back down to the facility roof deck. Now, in terms of equations and overall goals here, what we're trying to do is get that effluent up and away from the facility. So maximizing that plume rise is extremely important. So I mentioned this equation. This is the modified Briggs equation. This was used by ASHRAE up and through the 2010 and 2011 timeframe, but it's very appropriate to understand how and what makes it up, because it simplifies the whole point of what this goal is get that effluent up and away. And in the numerator, we have velocity and diameter. So that Z95, talking about 3,000 feet per minute or more, that would be the V component. In the diameter, the bigger the nozzle, the more mass flow of effluent coming out of that stack at a higher velocity is going to help get that effluent up and away from the facility. In the denominator, we have wind speed. And in this case, you can see wind going left to right across the page. Normally, I see engineers picking wind speed at about 10 miles per hour. But that's really based on your location. Some areas are windier than other. 10 might be a good average for your particular environment. But clearly, the more wind you have, the less overall plume rise you're going to have. Simply as what this photo, what this rendering is showing us here. It also allows you to put in your mind the pros and cons of using a variable frequency drive. And we're going to talk about that here shortly. As I increase velocity by increasing the frequency of the fan rotation, that plume is going to get higher. But if I'm in a situation in a lab where I want to use a variable frequency drive to slow down the fan to save a little energy, keep in mind that RPM is directly proportional to CFM and velocity. So the more you slow that fan down, the lower this numerator becomes, and that can become a problem on your building if the plume isn't high enough to safely evacuate the space on your roof deck. So modified Briggs, extremely easy. Too easy, apparently, because what ASHRAE has moved to is what's called momentum flux. Momentum flux isn't just one equation, it's pages of equations. I'm just showing you a handful of them here, and we won't go into much more gore. Outside of as you kind of pour through these equations, you're going to see some X variables. So what momentum flux gives us a point of height, but it also tells us what happens downstream laterally as the wind takes this effluent and moves it downwind. And that's valuable as well to us. The other item that they add is called terrain category. For your market, Atlanta, more urban, more buildings around our potential lab space that can have an impact on the plume, versus a facility that's out in West Texas with no other facilities. That's going to be more flat, desert type area where there's not a lot of obstructions. So these terrain categories can become factors that impact the overall plume. So what you would see with a momentum flux report out, and fortunately for us all, most fan manufacturers have this as embedded in their selection program. You would see a printout like this. In the x-axis, 0 to 120 feet downstream, the y-axis is overall plume rise. My stack would be at the origin. And there are a couple sets of curves that you will see. H sub x is as that air exits the discharge, and you can imagine a plume coming out of a stack and the wind is starting to carry it laterally across the ground. That's what H sub x is. So as we go 10, 20, 30 feet down, you can see the plume continues to rise, but it's again moving downstream. But what ends up happening is that H sub x could theoretically go up to infinity. So what ASHRAE and the momentum flux equations does is we put a cap factor. That's what H sub f is. And as you can see, as I get 60 to 70 feet downstream, this cap factor becomes what's in play. And in this case, it's just over 14 feet. When you're using a manufacturer's selection program and using the momentum flux, basically what you're going to get per NFPA is 10 feet of unit height, plus this 14 feet of plume, and it will say your effective plume height overall will be 24 feet. So that's how we use these equations to predict what that overall plume rise is going to be. Now, keep in mind, if you're using momentum flux and the Briggs equation, they're dramatically different in terms of that overall plume rise. Briggs was pretty simple. It didn't take into effect all of these other parameters. So what I found with Briggs and momentum flux is that the momentum flux is usually 25 to 30% lower overall plume rise than what Briggs showed. So if you're looking at both equations or comparing different types of products, make sure that you're using the same equations so that you're comparing apples to apples. Now, there are some neat things that the momentum flux brings us in terms of helping to understand concentration modeling. So plume is obviously important, but understanding how that plume disperses over time is important as well. So we've embedded what's called a ASHRAE plume concentration model in our selection program that uses the momentum flux. And you can see that same table here. We have downstream distance, plume rise. You can see where our stack would be here, and that black curve represents the curve coming from the momentum flux that we just discussed. And all these different color bands then represent how that chemical concentration disperses over time. So this grayish area is basically the boundary zone, less than 0%, I guess if you look at my legend here. And as we go from yellow to redder, there's higher concentrations of effluent. This is pretty handy, as if you look downstream, 60 to 120 feet and upwards of 30 to 35 feet above the roof deck, really this particular selection I have is pretty safe. If for some reason you have a receptor, 40 or 50 feet above the ground, you need to take a look at this selection and evaluate, do I need a taller stack? Do I need more velocity? Or do we have to make some other provisions to ensure this is a safe environment? Now, keep in mind, I put 10% concentration. That's high. Most of the time, the concentrations are quite low. And we'll talk about that a little bit more as we talk of the value of manifolded systems. But for sake of showing some colors, I put a high percentage in here so you can see how this all works. Now, this doesn't replace consulting a wind wake engineer to look at your particular facility, but it is a tool to get you off and running to ensure we have a safe environment around your lab facility. A little about the systems themselves. I have older lab designs, and we're going to talk about where we're going next with these manifold systems. Older lab designs, though, what you would end up is seeing these buildings with little fan farms up on top of the roof deck. So as you kind of burrow through and peel back the onion, you can go and see I have 50 chemical fume hoods. Each of them had their own riser that went up to the roof deck. Each of those had their own roof penetration and then a little fan up on top. So every hood has its own fan. And I guess the pros to that is if one of these hoods is underperforming, you could trace that up to the roof deck and maybe the belts aren't on, their fans off, and you make that adjustment and things are back up and running. So that's I guess that's the nice aspect of this. The downfall now is I have 50 little fans to take care of. I have 50 roof penetrations. And if you think about it in terms of that Briggs equation, where I said this is really a mass flow momentum problem, if you have one small fan dealing with one chemical fume hood, there's really not a lot of mass flow to get that effluent up and away from the facility. So that's really a problem with this, is that the plumes are pretty small and it ends up in an unsafe environment on top of that facility. So what we're seeing in general, this has really been going on over the last 20, 30 years, is the conversion of those individual fan and hood facilities to these manifolded exhaust systems. Again, I can have 50 hoods, but they're all tied into one exhaust manifold now. And instead of 50 little fans, I can have 2 or 3 bigger fans that can address that entire flow. So a few things come along for the ride, and we'll start with the plume rise. Bigger diameter, if you think about 3 times velocity times diameter, more or less fans, bigger diameter to handle all this flow, still attaining 3,000 feet per minute gives us a lot more mass flow momentum to get that effluent up and away from the facility. And I have less fans to maintain. I have less roof penetrations as well, all positives. And as you burrow back down inside of the building, the other thing that you find is that it's very rare for all of these chemical fume hoods to be in use at the same time. You know, usually a handful of them are open, others are closed. Some might even just have clean air going through, such that in many cases, by the time any contaminated effluent gets up to the fan, it's actually pretty well dilute. In fact, I see a lot of systems where they're using galvanized ductwork because the concentration of effluent is quite low. Now, what you have to be careful of is that whatever research in one hood is nice with the neighboring hood, right? So this research needs to be pretty compatible. So if you do find that you have a situation where things aren't compatible, you know, you pull them off to the side and you treat them different. So radioisotopes, perchloric acid, they'll have their own individual system off to the side. In this particular case, they'll have their own little exhaust fans up on top of the roof deck. But by and far, the more general stuff we can team up together like we're seeing on the right. And this is pretty much what I'm seeing on our laboratory spaces today. We'll talk a little about energy recovery, but you can easily imagine putting an energy recovery system on this high volume stuff to significantly save on the cost of operation of that system as well. Now that we know a little bit more about the manifolded systems, let's just talk quickly about constant, and then we're going to jump us across to our virtual lab to talk about variable volume systems. So constant volume systems are very simple. If we start by looking at my rendering on the right, I have an exhaust fan on the roof deck, I have a riser, and I have a chemical fume hood. So say this is a water treatment facility or even a school, very simple. When that fan is on, air is going to be coming through that chemical fume hood. And there are really no controls or things that change because the chemical fume hood has an air bypass grill. So when my sash is open, air just goes through that sash opening. As I start to close that sash, I get some mixture through the sash and through these bypass grills. And when my sash is completely closed, all of the air goes through the bypass grill. So really good for a small lab where hoods are not a big aspect of your ventilation system. Because as you can imagine, as I go from just a couple hoods to 20, 30, or 50 hoods, all of a sudden there is an incredible amount of air that's leaving my facility. And then I have to make all of that air up. So they can be very, very expensive to operate, especially markets like yours or up here in Wisconsin with very warm summers, cold winters. All of that air that's being exhausted has to be brought back in, heated, dehumidified, etc., which can be very, very expensive. So constant volume, a good solid approach, but again, it's generally for smaller labs, where that hood isn't going to be dominating your HVAC requirements. Variable volume hoods, a little bit different. Notice there is no more bypass grill here. So when that sash opens and closes, there are a number of different items that are adjusting to make sure that this system works. So sashes in general, 100 feet per minute is pretty typical going through that opening. So when my sash opens, I need more volume. And when that sash closes, I need less volume to maintain that safe 100 feet per minute. What I'm going to do here is jump across to our virtual lab. And give you 1 second for this to pop up. And what you will be seeing now are a bunch of red arrows and blue arrows all moving through my system. So in this virtual lab, we can do some neat things. I have sashes that can open and close. I have some AccuTrol valves above. I have a general exhaust, a snorkel. You can see a cabinet here with storage. All of my red arrows, my exhaust is being tied into this single manifold. And then we have an exhaust fan up on top of the building. So we'll talk about the exhaust fans and that aspect of it a little bit later. But let's just first concentrate on what's going on inside of the space. Over on the right, you can see my blue arrows are air that's been conditioned for that space. So there are 3 control loops that we're monitoring here. One is the pressure of the lab. So I have more red arrows going out of the space than blue arrows because I want this lab to be slightly negative. So just a little bit more exhaust than what's coming in. So prevents any odors, fumes from exfiltrating to the rest of the building by keeping my lab space negative. And that's pretty common. I guess that you could have a situation where you have a clean room lab and things will be different, but most time it's negative. The second control loop then has to do with the airflow going through my chemical fume hood. So I showed you how we can open and close that sash. You can see this little valve can open and close above that unit. So the easiest description of this is that I would have a sash sensor. When my sash is open, it tells this little damper or little valve what position it needs to be in to provide the appropriate flow of air to maintain 100 feet per minute or whatever safe velocity you have for that particular hood. When I close the sash, that valve shuts down, not totally, but enough to allow a small amount of air that's still opening. You can see on all 3 of these, it all occurs the same. So that's my second control loop, is monitoring and controlling that velocity. So a sash sensor, and it can also be a velocity sensor going through. So you'd have more of a, I guess, a closed loop system in that particular case. Now, the last is the duct static pressure. So if you've been observing here when I've been opening and closing sashes, there's a little bright light here that has been turning from green to red, indicating a change. So in my lab, green is good. That means my duct static pressure is appropriate to provide pull as needed when these sashes open, or when the sashes are closed, that there's not too much pressure drop in that duct. So right now at 100% open in my chemical fume hoods, my fan is balanced, it's pulling the air, it's creating the plume, everything's where it needs to be. But as I close a sash, that valve closes, I go red for a second because my fan is on top of the facility trying to pull air from this lab, but there's less air available since these valves are closing when the sash is closed. So to deal with that in a traditional variable volume system, what we do is introduce bypass air that comes in from outside adjacent to the fan to make up for what's not coming in from the lab space. And that bypass air comes through what's called a bypass damper, and it's in a bypass plenum. So that bypass plenum assembly is a critical component because it allows us to mix in outside air with the laboratory air to make sure that this light stays green as much as possible. So when I close the sash, we'll bring in outside air. When that sash opens back up and we need more contaminant from inside the building, that damper is going to be closing down, all triggered off our building management system, which is monitoring this duct pressure. So all day long, as sashes open and close, this damper is going to modulate to ensure that we keep this green light green and avoid overpressurization or underpressurization in that space. So that's the common approach to operate these types of systems. Now, you could, as I mentioned before, use a variable frequency drive. So I mentioned VFDs when we were talking about plume rise. So what you could set up your controls to do is, as I close a sash or two, instead of using bypass air, you could just say, hey, I'm just going to turn this fan down because I need less air now because there's less air coming out of the space. And all certainly possible to do. What you just have to be aware of, again, as you slow the fan from 60 hertz to 50 hertz or 40 hertz, that nozzle velocity will be impacted as well. And when that nozzle velocity goes down, just as the Briggs equation told us, that plume rise is going to go down as well. So be careful of that. I think it's a safe thing to do as long as you don't go too low on your overall plume. And it's pretty common practice nowadays. And probably more I'm seeing now is a combination of RPM control, and then when you hit that minimum RPM threshold, using the bypass damper to balance everything off. Now, we said we'd talk a few minutes about the fans. So I'm going to show you the most common style of fan first that we're seeing with these laboratory systems. This is called a high plume dilution inline fan. So it's inline, and as we work through, you can see our air is coming into the base of our bypass plenum. It could certainly come horizontally into this plenum as well, no problem. Goes up to an isolation damper, and as the fan turns on, that isolation damper turns on. You want the motor of the fan and the actuator to be tied together. They both open together, they shut off together. That's a good practice. Air is going inline to the fan body, and it goes up into the nozzle and the wind band. So the nozzle in this case is a very high velocity nozzle to help provide dilution air. See all these green arrows that are coming in from around the wind band to mix with the effluent. So the whole idea of these high plume dilution nozzles and wind bands is to dilute the effluent before it exits the top of the wind band. Now, this is cool in the sense that if you have high concentrations of odors or effluent, it's much more dilute when it leaves. And that's a good thing, especially if you have a makeup air system that's adjacent to your fans, or you have some receptor of air intake and the wind tends to be blowing that direction. So it creates concern for you. That's the positive of this type of system. The challenge is that to create dilution, you have very, very high nozzle velocities. And I see velocities from different manufacturers of 5,000 to over 7,000 feet per minute. In this particular case, I selected this fan at 6,000 feet per minute of nozzle velocity. You know, just like anything, if you make ductworks that go from 2,000 feet per minute to 6,000 feet per minute, it creates challenges, more pressure drop, more sound, more horsepower requirement. So you have to be aware with this type of fan, while it does give you the benefit of dilution, it might cost you in terms of energy and sound. So just make sure you make a good selection and don't become enamored with very high plume rises and high dilution, because there's a price to pay for that. But if you're in a situation where it's a life safety, you have to make that call and make that decision. Now, the alternative I'm seeing in terms of nozzles is going away from dilution to what we simply call a high plume nozzle. No dilution, one-to-one airflow pattern in and out of that particular nozzle. So in this case, 12,000 CF into the fan, 12,000 coming out of the nozzle. Generally, what I find with this type of nozzle is that I can get equal or better plume rise, which is one of our key goals, but it uses 1 to 2 motor sizes less. So your capital expenditure goes down, your long-term operating costs go down. And that's really important for the owners to save that energy over time. So this is another good solution. It offers some VE opportunities and keeps your facility safe as well. So keep that type of nozzle in mind. And then lastly, we have what's called variable geometry nozzles. Variable geometry nozzles are unique in that the nozzle can adjust its area in flight. So I mentioned variable frequency drives, and as you slow that drive down, those blades, or excuse me, on a fixed nozzle, your velocity is going to decrease. But if your blades can adjust in flight, you can control that area by monitoring the fan flow and let the blades fall in an area to maintain 3,000 feet per minute or 4,000 or whatever you're looking to achieve. So keep that in mind as well. So circling back on the fans again, I had mentioned this to be an inline fan. The alternative to an inline fan is a centrifugal fan. Both styles are used on labs all across North America. They work great. It's just more of a preference. Again, with a centrifugal style, I can have my bypass damper in my fan. My bypass damper opens and closes to make sure that green light stays green and that my pressurization is correct. No changes there at all. You can see air can come up through the base. It can come horizontally into that plenum. You can see my rotating impeller. In this particular case, I have a high plume nozzle and that air is going up and above the product. I guess if you were to think about any pros and cons, the advantage with the centrifugal systems is access. Everything's at roof deck level. The disadvantage is real estate. The fan and the plenums are adjacent to each other, so they take up more roof deck space. When I go back to an inline fan, you'll see these are more like a skyscraper. This is, downtown Atlanta. They don't take up a lot of footprint. Serviceability can become a challenge because the motor is 6 to 8 feet off the deck. So on roofs with a lot of HVAC stuff, other ducts, fans, blah, 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 these fit into those areas very, very well. All right, so I'm going to jump back to our presentation and we will get back on to more about the products and best practices. Best practices, as I had mentioned earlier, things that we run across as we work on a lot of laboratory systems. And I like this photo on the left. It just gives you a feel for how big these systems. This is not an unusually short gentleman. He is standing next to the bypass plenum. This was a semiconductor facility in the Minneapolis area. But again, we talk about NFPA 45 and 10 feet. This system had no problem getting past the 10 feet. But as you look at like the locations of the motors, obviously having the access here for ladders or scaffolding, all of that's really, really important. So, a lot of what I'm going to talk about is pretty, fundamental, makes a lot of sense, but you have to be thinking about that as you're laying out your roof decks and understanding what's going on around your equipment, in this case for serviceability. So, first thing I think is very important is just to keep in mind the value of pre-engineered versus field fab systems. As a fan manufacturer, we do both. We have pre-engineered lab systems and we make utility sets like I'm showing here. And this is my West Texas layout where you can see there is literally nothing behind this particular facility. So in this case, we had a couple small constant volume labs with utility sets. And as I go around and talk to engineers, I see this laid out very, very commonly where I have a utility set, I have a stack, but on the drawings, it's usually a beautiful curved duct. It doesn't have a box with a hole cut out of it. It doesn't have an inexplicable elevation change. So the reality of these field fab systems is from paper to what ends up on the roof deck, in a lot of cases changes. And for these two fans, which were set up to do 1,000 CFM, 1,000 turned into 750 because I had a 15% pressure drop right here and a 10% loss because of that elevation change. What that ended up, and then is 2 to 3 weeks of the engineer, our rep, fan manufacturer, all figuring out how to fix the problem. And the way they fixed the problem is they bought new motors and drives to overcome the deficiencies of the system. Forever, that owner is going to pay more on energy and the sound is louder. So it's not going to go away. Now, the idea of pre-engineered is that as manufacturers now, we can take care of all of the stuff above the roof deck. But if we know your flow requirement, the external static pressure from your process to our curb, we can accommodate the isolation dampers, the nozzle pressure drop, if there's energy recovery. Anything as part or inherent to our system is part of what makes up our fan curves now. So we don't run into the risk of losing, 25% of the full performance as we did with this field system. So from an engineering perspective, the selection process is much easier. It's all certified. From the contractor perspective, much easier to assemble. In this case, just plunking and dunking on the roof, tying that curb down, no guy wires. And then for all of us, that commissioning process, we want that system up and running quick so we all can move on to the next job. So this pre-engineered systems is a great way to go. And again, the intent here is to make it simpler on everybody, plus give us a safe operating system when it's all said and done. And as I showed you on the virtual lab, inline fans, centrifugal fans, whatever your preference is, belt drive, direct drive, you have there's a number of different solutions that can be used there. All of these nozzles are interchangeable. So again, working with Holden Associates to get the appropriate product, they'll definitely point you in the right direction on what works for your facility. Now, acoustics comes up a lot. And I like this picture because it shows, more than what everybody tends to think about in terms of sound. Indoor, outdoor, and radiated sound. So normally what you see from the industry is outlet sound, like what's up here. And I would contend most people are not spending a lot of their time above a laboratory exhaust fan. Most of the time it's the people below inside of the facility, or it's the neighbors that are kind of perpendicular to this particular facility. So knowing outlet is good, it's informational, but knowing radiated sound and what's breaking off from the motors, what's coming out of the damper is important as well. So we have a lot of different means to treat all of this sound. And probably the most common thing anyone would think about is an inline attenuator. Definitely a solution to help with that outlet sound, and attenuated wind bands as well. Anything coming out of the top of the system, there are solutions to take care of that. In terms of bypass attenuation, you can see this little unit here. So this is an attenuator for the bypass damper. So when you look at bypass dampers, they can handle anywhere from 50 to 75%. They can handle 50, 75% of the total lab exhaust. So if I have a 50,000 CFM lab, my nights and weekends, I could have 25 or 35,000 CFM coming in through this bypass damper, and that can actually become a problem where that sound dominates the fan sound. So when you have those systems where I have significant changes in lab flow and I'm bypassing all of that air, keep these attenuated bypass weather hoods in your mindset as well. For the 2000 CFM system, it's not worth it. This is more the 30, 40,000 CFM systems where you can have a significant bypass problem. But when it all comes down to it, what I've seen in the past, while we can treat a lot of that fan sound, one of the best overall means to protect the landscape around your particular facilities are these screen walls. So here are the fans, obviously, you can see them, and the manifolded duct leading in. Say that the president of the university is adjacent or downstream here. Having this screen wall traps that sound in on top of the building, and if anything, it goes up. Now, this is not a solution you add after the system is up and running. So if you are laying out a job and it's sound sensitive, we'll do all we can on the fan side to help keep that under control, making a great selection, providing whatever attenuation means is possible. But if it's a real concern, you want to consider, in this case, it's just even a partial sound to prevent anything that's going off the back of the page in this particular case or over to the right. It works really, really well. Other areas that I see pop up are sound inside of the building as well. So, and I see this primarily in smaller, maybe single-story hospitals, clinics, maybe compounding pharmacies where the fans are not that far away from where the actual chemical fume is. And maybe it has a little bit higher pressure. So the fans are running a little bit faster. There might be a little bit smaller, where maybe 71 or 72 decibels from the fan doesn't seem like a lot, but it goes back into the space and become a problem for the researcher. So while as a fan manufacturer, we always preach, straight ductwork, it's the best way to go, and, eliminate system effects. What I'd recommend for those smaller facilities is that you actually have a couple breaks and elbows in the ductwork. And maybe you actually put some packless silencers or elbow silencers in there as well. So the sound doesn't just shoot right down into the system and become an irritant for the people within the space. Help treat some of that sound, get that 72 decibel down to 65 or 64 so that it doesn't become a problem, again, for the researchers inside of the space. Much more difficult to make changes like this afterwards, but it's a good practice to think about it prior to the installation, again, for helping the sound inside of that space. Structure. Another thing that I've seen over the years, which can become a real challenge. Many of these buildings are old, so we're adding dunnage and other things to hold big systems up on top of the building. If you have not seen this particular guide, this is called Noise and Vibration Control for HVAC Systems. It's an ASHRAE document. It's a great book written by Mark Schaefer. So pick it up if you haven't seen it or read it. It's a great document. One of the things they talk about, though, is structure. And I'm using the term dunnage, I guess, roof. This is steel that's mounted up on top of the roof deck to hold equipment. And, as you look through his photos, it all sort of makes a lot of sense. The more structure you have underneath vibrating equipment, the better. Way up in the upper left, the trampoline is not a good solution where that fan can actually trampoline and cause vibrations inside of the facility. So generally speaking, more structure is better, and common sense. But we don't always see that happen on some of these facilities, especially, again, older buildings that are being retrofitted with big equipment, where they've gone from the little, you know, the fan farms, 50 little fans, to 2 or 3 bigger fans, which have much more weight and a little more challenging. It's a concentrated load. But what I'm going to show you here is a situation that we had, where we had 3 large inline fans up on top of the facility, and you can see the dunnage and structure around, you know, looks really, really good. But what, as we found out, is it had the poor type of structure, where all of the perimeter, it has support, but there was no support to the entry or to the center of the section. So it was operating like a large trampoline, and it was causing vibrations to go back into the building. So we actually went out and monitored this facility, and we put accelerometers all around that, the framework that's holding up the particular equipment. And I think I can get this working here. Basically, and while it wasn't to the point you could literally see these dancing up on top of the building, but there was a small vibration in the center of this particular facility. It was again translating and going back into the system and causing problems inside of the facility. Nobody likes vibrations, nobody likes sound, so it's something that needed to be treated. And the only solution that they had to treat these was to add more structure to prevent that trampolining effect. Again, many of these things are hard to fix after the fact. So keeping that in mind, if you're using dunnage or dealing with sound, you know, placement, making sure you have appropriate structure, adding those screen walls, all can be things that can save you time down the road and prevent any problems. Invasive flow stations. This is popular as well, and this really came out with the green, the lead. Everybody wants to know how much air is coming in and out of their equipment. And on the laboratory exhaust side, I see a lot of customers that are actually tracking nozzle velocity to make sure it's safe. So one means to track the velocity coming out of the fan is measuring how much air is coming into the fan. So we see this installation of flow probes in the venturi, and that's the venturi and a wheel in the background. But these flow probes kind of get plugged into that venturi, and that they know that area, they can calculate the velocity and go through the math to tell you what the airflow is. So what we found with these is not the biggest thing is they provide a measurement, but they significantly impact the flow of air going through that venturi. You might have a 15 to 20% reduction in flow, which, you know, kind of defeats the whole purpose. We want to save energy and monitor it, but we're going to use more energy to overcome these probes. So the alternate are called piezometer rings. A piezometer ring is a differential pressure reading across that same venturi. So know the pressure leading into the venturi, and then we have probes that measure the pressure at the highest velocity of that venturi. And it's a calibrated nozzle. It's very easy to calculate an equation like we're seeing here on the right, where CFM is equal to, in this case, 3825 times the square root of that change in pressure divided by density. So very easy for the test and balance staff to understand how much flow. You can plug electronics into this to understand the flow of that system. It works great. Know your velocities, no pressure drop, it works. Pretty much all fan manufacturers have this option now. So good thing to have in your specifications, airflow monitoring, and make it non-invasive. Use these piezometer rings. They work really, really well. This one's pretty obvious. Keeping that ductwork straight and lower velocities. So in this case, a beautiful installation, and, you know, seemingly right up to the fan, they had nice level duct, but inexplicable elevation changes up, down, and that air is, you know, now it's coming at a downward trajectory and swirling before it goes up through the fan. So, you know, keeping your velocities under 1,500 feet per minute if at all possible, keeping the flow straight, all of that prevents field issues. It prevents excess pressure drop, which helps keep the energy cost down as well. So all fundamental stuff that'll put you in the right direction when you're laying out your systems. And then finally, applying energy recovery when possible. I mentioned energy recovery when we talked about manifolded systems, and I'll show you some of the code changes here as we wrap up here in a couple minutes. But on your bigger lab systems and even your smaller lab systems now, there's more capital friendly solutions for collecting energy out of your exhaust side. So in this case, you can see I have my lab exhaust fan. Here's my bypass plenum. And what we're doing is integrating a coil, run around coil loop, and we have a coil on the supply side. So Wisconsin winter, it's 0 degrees outside. We want to take a little bit of that 70-degree exhaust and heat up that air that comes into the space. So for markets with big delta T, your markets, our markets, it's a great solution. And it starts to become more and more viable as these systems get bigger and you can offset the cost of the exhaust box and coil. So great thing to do, saves energy. And actually, you're going to see more and more of this as a requirement as the codes start to change and try to figure out how to reduce that cost of operation in the lab, which gets me to the wrap-up portion here. So history direction, what are we seeing? And I guess it'd be 3 weeks ago now, I was in Toronto for ASHRAE. And this fall, I2SL will be in Pittsburgh. So, there are a lot of great things going on in ASHRAE. If you do a lot of labs, I2SL in Pittsburgh in the mid-October, check it out. It's a great thing to spend. It's a couple days. It's a great program related to labs. But you can see what's all going on in the world. The 3,000 feet per minute, I say going away. It's gone. If you look at ANSI Z9.5, and again, that's coming down to maybe you don't need 3,000 feet per minute. Maybe your system allows you to go to 2,500, and that can save some energy. But ultimately, we want it to be safe. I talked about the conversion to variable air volume systems, which is great. Less air out as I shut these sashes means less air in that has to be heated, cooled, humidified. Huge energy savings for the lab owners in that particular case. We talked about avoiding excess bypass air, using variable frequency drives to slow the fan down. There's other techniques we can talk about later in future presentations. Talked about VFD, speed control, again, going hand in hand with reducing bypass. We talked about energy recovery. Now, the next couple that I'm showing here, wind speed, wind direction, concentration, that's really where the market's heading next. Understanding what's in the lab space, the concentration. So maybe somebody spills and there's a high concentration of effluent. We are definitely concerned then of what's in that environment and what's downstream, especially when the wind's blowing towards our air intakes. What if the wind does a 180 and blows right to left and it's West Texas and there's nothing out here? Well, maybe we're not as concerned as much as maximizing that plume rise and we're okay shutting the system down. So in other words, we're going to be monitoring more and more stuff, analyzing all of this stuff and making sure that the system is doing appropriate things for the number one, make it safe, and then reduce the cost of energy for that particular facility. So that's changing. When I look at the main regulation, we talked about Z9.5, we're not going to go into that more. ASHRAE 91, this is going to impact your lives, especially as you roll into 2019. FEIs of 1.0 on all fans, including your lab fans, is going to make better initial fan selections. If you do any work for California, the California Energy Commission has been busy following the Z9.5. They're looking at the watts per CFM. And then if you don't meet these watts per CFM, they will actually have you look at the wind direction monitoring and chemical concentration monitoring as well. So they're really jumping into that new technology. And then what we're seeing is some pretty significant activity in the Department of Energy. That's to be determined, but from what I'm seeing, they're looking to spend a lot of time with regulation of the fan industry, which is going to change, the types of fans we offer and how we select those fans to keep the energy consumption down. So look forward to those changes coming down the line, especially on the DOE. And then finally, before I pass it back over to Tracy, we do have additional lab presentations that go more into these control strategies, energy recovery, the chemical concentration monitoring as well. So if that's something of interest, obviously get in touch with the Holden team and we can help set that up and to go into more detail on ways to safely and efficiently operate your lab space. So Tracy, I'm going to pass it back over to you.